I want you to visualize something straight out of a science fiction movie. Think about the device you are using to listen to this right now. You know, a phone, a computer,
Oh,
whatever.
right, your everyday tech.
Exactly. And inside that device is a processor, and it's bolted to a motherboard tangled in this microscopic web of wires, and it's generating heat you can literally feel on your lap or in your hand.
Yeah, lots of heat, lots of physical connections.
But now I want you to just strip all of that away. Picture a computer processor floating, completely untethered. It is perfectly still, suspended in a total vacuum, and it's operating at temperatures hovering just a fraction of a degree above absolute zero.
It really is a striking image, isn't it? I mean, total, profound isolation, a computational brain with just no physical connection to the outside world whatsoever.
It is wild. And today's deep dive into our sources is about a document outlining exactly how to build that isolated brain. We're looking at the revised blueprint for an architecture called the Quantum Sphere V2.0.
Yes, the infamous version 2.0.
Right, because this is a radical new engineering roadmap for quantum computing. But, you know, it is also a story about honesty and rigorous peer review in science.
Oh, absolutely. The peer review aspect is huge here.
Because version 1.0 of this design, it had some, well, mathematically embarrassing and physically impossible errors in it. And version 2.0 fixes them.
It really does. It presents a viable roadmap to replace those massive, power-hungry dilution refrigerators that current quantum computers basically rely on.
Yeah, swapping them out for this elegant levitating core. Okay, let's unpack this, starting with the biggest, most glaring problem the V2.0 roadmap had to fix, which is the outer shell.
Right, because to appreciate why this floating core is even necessary, we really need to look at the hostile environment quantum computers currently live in.
Right, the noise.
Exactly, the noise. The quantum bits or qubits that run these systems are incredibly fragile. I mean, they are plagued by the noise of the universe.
Like what kind of noise specifically?
Oh, everything. Magnetic fields from the Earth, thermal leakage, even the microscopic mechanical vibration of someone literally just walking down the hall can destroy a quantum calculation.
Which is crazy to think about. Just footsteps ruining a supercomputer.
It is. And to fight that, the industry standard has been to build these massive dilution refrigerators. If you've seen photos of them, they look like giant, intricate golden chandeliers.
Oh, yeah. They look amazing. But they're huge.
Huge, and made of wires and copper plates, drawing between 10 and 26 kilowatts of power, all just to shield this tiny chip at the very bottom.
And the quantum sphere proposes something entirely different, right? Instead of building a bigger refrigerator, they want to change the fundamental geometry of the computer itself.
Right, they want to change the shape.
And their solution is the spherical Hallback shell, which, I will be honest, sounds like a magical artifact from a fantasy novel.
I mean, the terminology is definitely colorful, but the physics is very established. A Hallback array is just a specialized arrangement of magnets. The geometry is mathematically tuned so that the magnetic field is intensely concentrated on one side of the array, while on the opposite side, the fields basically cancel each other out almost completely.
Oh, interesting.
You actually interact with a very simple, flat version of this all the time. Think of the magnets on your refrigerator.
Oh, really?
Yeah. They stick forcefully to the metal door, but if you wave your hand behind them, on the other side, you feel barely any magnetic pull at all.
Okay, I see. So if you take that flat array and you sort of wrap it into a continuous three-dimensional sphere, you create a bubble.
Exactly, a magnetic bubble.
You get this perfectly uniform, highly controlled magnetic field inside the hollow central cavity and practically zero magnetic field leaking out. It basically becomes a fortress against external magnetic noise.
That is the goal. It isolates the delicate qubits from interference without needing a massive room-sized rig. But as you mentioned earlier, the initial proposal for how to build this fortress, the V1.0 document, it contained a catastrophic miscalculation.
Oh man, it sure did.
The original design stated they would generate this shielding magnetic field by running massive electrical currents through a spherical shell made of laser-reduced graphene oxide.
Which sounds incredibly advanced, right? Until you actually sit down and do the math. To give you an idea of how absurd this was, we really have to look at electrical resistance.
Right, because the V1.0 design required a magnetic field of 0.2 Tesla.
And to generate a field that strong, you have to push an immense amount of current through the shell. Trying to push that much current through a material like graphene oxide, it's like trying to fire a high-pressure fire hose through a tiny plastic drinking straw.
Yeah, the resistance would just be off the chart.
Exactly. The electrical resistance would be astronomically high. It would dissipate roughly 60 billion watts of heat per square meter.
Which is just, I mean, it's physically impossible.
That is. You are trying to cool a system to near absolute zero, and your shell is generating enough heat to vaporize solid steel instantly.
The heat generation was something like 11 orders of magnitude beyond their allowable thermal budget. It was a fatal flaw.
But then we get to the V2.0 fix.
Right, the V2.0 fix is what brings this whole thing back to reality. The engineers kept the graphene, but they were finally honest about its physical limitations.
So what do they do instead?
Well, in the revised design, the structural shell is a 3D printed graphene oxide aerogel.
An aerogel?
Yeah, an aerogel is essentially a solid material where the liquid component has been replaced with gas, making it incredibly lightweight.
Oh, wow.
And it spreads heat beautifully and absorbs electromagnetic interference. It makes a perfect scaffold. But for the actual electrical current, they switched to sputtered superconducting niobium traces.
And niobium is the key here because it is a superconductor at those incredibly low temperatures, specifically right around 4 Kelvin.
Exactly.
Because when a material superconducts, it loses all electrical resistance. The electrons just pair up and glide through the material without bouncing off the atomic lattice at all.
And that changes the entire equation. Because the niobium traces are superconducting, they can carry those massive, persistent currents to generate the Hallback field with absolutely zero heat dissipation.
So the fire hose is no longer being forced through a plastic straw.
Right, it's flowing through a frictionless vacuum tube. The thermal problem is completely solved.
But the engineers also realized they didn't even need that massive 0.2 Tesla magnetic field in the first place, right? Because of the specific type of quantum brain they were putting inside the sphere.
Exactly. The system is optimized for a very specific, highly advanced type of qubit. They are called Kramer's pair, or spin valley qubits, and they are housed in a bilayer-graphene processor.
Okay, that sounds like a mouthful.
It is, but it's a crucial pivot. Standard qubits often require a very strong external magnetic field. The field acts as a sort of wedge, splitting the energy levels of the quantum states so the computer can actually differentiate between a 0 and a 1.
Right.
But generating that wedge requires massive currents, which, of course, invites noise.
So how do Kramer's pair qubits bypass that?
By utilizing the intrinsic properties of the bilayer graphene itself. Without getting too bogged down in the quantum mechanics here, these qubits use something called time reversal symmetry.
Yeah.
They have natural energy states based on the quote-unquote valley and spin of the electrons. They literally don't need a magnetic wedge to function.
Wait, really?
Yeah. In fact, a strong external magnetic field actually scrambles their natural protection. They thrive when the magnetic field is as close to 0 as possible.
Wow, so that makes the engineering so much easier.
Yeah.
The shell doesn't need to generate a crushing 0.2 Tesla field anymore. It just needs a tiny millitesla scale bias field for fine-tuning.
Exactly.
Its primary job is simply to act as a shield to block out the Earth's magnetic field and the buzz of all the lab equipment.
And taking that immense pressure off the conductor system is what makes the rest of the architecture even possible.
Okay, so let's picture where we are now. We have this perfectly isolated 3D printed superconducting spherical shell. It's blocking out the noise of the universe, but what goes inside?
Right, the core.
Because we've completely isolated this cavity, but we still have to figure out how to keep external physical vibrations from sneaking in and ruining those fragile quantum states.
And this brings us to the levitated core. In the flawed V1.0 roadmap, the plan was to hold the processor chip in the exact center of the sphere using graphene nanoribbon tethers.
Like physical strings.
Exactly. Imagine microscopic struts physically tying the chip to the inside of the shell. But a fundamental rule of quantum isolation is that any physical tether, no matter how microscopically thin, is a bridge.
A bridge for phonons.
Yes.
For those listening who might not be familiar, a phonon is essentially a unit of mechanical vibration or heat. Like if you pluck a guitar string, the vibration travels down the string.
Right.
So if someone walks heavily in the laboratory above, that physical vibration travels down through the building into the shell and right across those physical tethers into the quantum chip.
And beyond just vibration, those physical clamps introduce something called dielectric loss. Well, when a quantum circuit is holding information, it is essentially oscillating electrical energy. If a physical tether clamps onto that circuit, the electrical field actually penetrates the material of the tether itself.
Oh, I see.
And the atoms in the clamp start to jiggle, absorbing the quantum energy like a sponge and converting it into heat. You are literally bleeding your quantum information away into the physical struts holding the chip up.
That's terrible.
Well,
So if we can't use physical strings, we have to use invisible ones. Are we talking about magnetic suspension here?
we are. V2.0 removes the tethers entirely by utilizing Meissner levitation.
Okay, Meissner levitation.
Yeah, so the bilayer-graphene processor chip has a closed, superconducting niobium ring built right around its perimeter.
Right.
And at the top and bottom of the spherical shell, the north and south poles, there are trap coils. These coils create a specific magnetic landscape inside the sphere that has a sort of valley, a minimum point of magnetic strength, right in the dead center of the cavity.
And because the niobium ring on the processor is a superconductor, it actively fights back against magnetic fields.
That is the Meissner effect in action. A superconductor violently expels magnetic flux, so the ring naturally seeks out the weakest magnetic point in the room to minimize the pressure on itself.
That is so elegant.
It really is. It just nestles right into that magnetic valley at the center of the sphere and floats there, perfectly suspended in all three dimensions.
What's fascinating to me is the scale of this. The document notes they are levitating a 1 milligram processor die using a magnetic field of just 5 millitesla. I mean, it is a microscopic amount of force holding this brain in the void.
What's fascinating here is how this entirely sidesteps a classic rule of physics called Earnshaw's theorem.
Remind me what that is.
Earnshaw's theorem dictates that you cannot stably levitate a regular permanent magnet using just other static magnets. The forces will never perfectly balance. The levitating magnet will always eventually flip over or slide away.
Like trying to balance a pencil on its very tip. But Earnshaw's theorem has an exemption, doesn't it? It doesn't apply to superconductors.
Right, because a superconductor isn't a static magnet. It actively reacts. If the chip drifts slightly to the left, it encounters a stronger magnetic field from the trap coils.
And then it pushes back.
Exactly. The superconductor pushes back against that stronger field, creating a restoring force that shoves it back to the center. It creates a completely stable, self-correcting magnetic bowl for the chip to rest in.
I do have to play devil's advocate here, though.
Go for it.
If this processor is just floating in a magnetic ball, it's still going to have microscopic jitters. I mean, we are talking about quantum calculations where the slightest drift could ruin the computation. How do we keep it perfectly still without touching it?
That's a great point. The design incorporates an optical port for interferometric position monitoring.
Okay.
Simply put, they bounce an incredibly weak laser off the chip to measure its exact position down to the micron.
Wow, down to the micron.
Yes. And if the monitoring system detects that the chip is starting to drift, it feeds tiny electrical trim currents into those trap coils at the poles. It slightly shifts the magnetic bowl to nudge the chip back into perfect alignment.
But wait, hold on. Doesn't sending those corrective signals, doesn't that create the exact kind of electromagnetic noise we just spent all this time trying to block out?
It would, under normal circumstances. But the brilliance here lies in the vast difference in scale. They operate the servo, those corrective electrical nudges, at frequencies well below 1 kilohertz.
Oh, I see.
It's a very slow, gentle rolling motion. The quantum bits on the processor, however, operate at gigahertz frequencies.
Right.
They are oscillating millions of times faster than the physical nudges. Because there's such a massive chasm between the frequency of the physical correction and the frequency of the quantum information, the qubits completely ignore the movement. The servo doesn't cause any decoherence.
Okay, that is incredibly clever. But because we've completely isolated this chip in a vacuum to protect it, we've inadvertently created a massive new problem. The chip is trapped. Here's where it's really interesting.
Oh, absolutely.
Because how do you communicate with a computer when you are physically barred from plugging wire into it? And worse, how do you keep it from overheating if there's no physical heat sink?
Well, it becomes the ultimate wireless device. The system relies entirely on fully wireless microwave links, bridging the microscopic 10 to 100 micrometer vacuum gap between the shell and the floating chip.
Yeah, the document details this process using capacitive and inductive coupling. For anyone who hasn't taken an electromagnetics class recently, think of two tuning forks placed across a room from each other.
Right, resonance.
Exactly.
Yeah.
If you strike one fork, the sound waves cross the room and cause the second fork to start vibrating at the exact same frequency,
Yeah.
without them ever physically touching.
That is a perfect analogy. Capacitive coupling uses electric fields, like two metal plates facing each other across the gap. Inductive coupling uses magnetic fields, kind of like two coils of wire.
Right.
So the shell has superconducting resonators that act like that first tuning fork. They broadcast microwave pulses across the vacuum. The circuits on the floating chip catch those invisible fields to receive instructions for the qubits and then broadcast the results back out.
And they don't even use physical wires for direct current power, right?
No, not at all. The system literally trickle charges the on-chip power reservoirs using a dedicated, continuous microwave tone.
It's like a hyper-advanced version of dropping your smartphone onto a wireless charging pad. But this raises the most terrifying constraint in the entire document.
The heat.
The heat. If you are blasting this floating chip with microwave energy to power it, and it has absolutely no physical wires to dump heat away, where does the heat go? I mean, think about a high-end gaming laptop. It relies on copper heat pipes, physically transferring heat away from the processor to a spinning fan. This floating core has none of that.
Right. Heat can only escape through what are called single-mode photonic heat channels. Since conduction through solid matter is impossible in a vacuum, the heat generated on the chip must radiate away as electromagnetic energy, as photons, literally jumping across the vacuum gap to be absorbed by the colder shell.
And if you're wondering how efficient that is, it's brutal.
Oh, it's incredibly restrictive.
At these unimaginably low temperatures, right around 100 millikelvin, the document states that 10 of these engineered photonic channels can only extract about 5 times 10 to the negative 14 watts of heat.
Yeah, so to make this entire architecture viable, the absolute maximum heat generated by the floating chip cannot exceed 0.1 to 1 picowatt.
A picowatt.
A picowatt is 1/trillionth of a watt.
If you're wondering how small a picowatt is, imagine trying to cool down an entire massive Amazon data center by blowing air through a single tiny keyhole. The bottleneck is just absolute.
It really is. The picowatt limit is the central, non-negotiable engineering constraint of the V2.0 design. It dictates that every single component on that floating ship must be electrostatic or superconducting.
Because any resistance would ruin it.
Exactly. Any component that generates electrical resistance would instantly melt the thermal budget. It also means the qubits themselves must be incredibly stable.
Ah, going back to the Kramer's pair qubits.
Yes, remember those. They have a relaxation time of around 30 seconds. In the frantic, hyper-fast quantum world, 30 seconds is an absolute eternity.
So they don't need constant fixing.
Right, they require very little active maintenance or corrective pulsing, which keeps the overall heat generation incredibly low.
But even with all that miraculous efficiency, we still have to get the temperature of that chip down to 100 millikelvin to begin with. And we completely threw out that massive 26 kilowatt dilution refrigerator in the beginning. So how does a floating chip stay cold?
Well, the V2.0 roadmap introduces autonomous quantum absorption refrigerators built directly onto the chip.
Built onto the chip itself.
Yeah. So the outer spherical shell is cooled to 4 Kelvin using a standard pulse tube cryocooler, which is a much simpler off-the-shelf cooling technology. But to get the floating chip down to the millikelvin range, they use thermodynamics in a way that feels almost counterintuitive.
I have to push back here. Wait, hold on.
Sure.
The document says they drive these refrigerators using wireless microwave noise sent from the outer shell. You're telling me they are blasting this highly sensitive, isolated quantum chip with random microwave noise.
That's exactly what they were doing.
Doesn't noise instantly destroy quantum coherence? And how does absorbing energy make something colder?
I know, it sounds crazy, but it is a brilliant piece of physics. These absorption refrigerators are specialized 3-level superconducting circuits. They don't interact with the qubit-specific frequencies, so the noise doesn't actually cause decoherence.
Oh, I see. They are on different channels, basically.
Essentially, yes. Think of the refrigerator like a thermodynamic water wheel. The microwave noise from the shell acts as a heavy flow of high-energy water falling on the wheel.
Okay, I'm picturing it.
The circuit absorbs a high-energy photon from the noise. It uses that massive energy state to force a transition that actively absorbs a low-energy packet of heat away from the qubits.
Wow.
It combines them and then dumps a slightly higher energy photon out to the hot reservoir, radiating it right across the vacuum gap.
So the heavy flow of noise is providing the physical work required to pump the tiny trickle of heat uphill and off the chip. It is cooling the processor, using wireless noise. That is staggering.
It is. It sounds like pure theory, which brings up the skepticism you'd naturally feel reading this. Is this just a pipe dream living on a PDF, or is someone actually building this?
Well, the V1.0 document confidently laid out a timeline of 3 to 6 months to build a working qubit prototype. I definitely chuckled when I read that. 3 months to completely reinvent quantum physics. Sorry.
Yeah, it was a timeline completely divorced from reality. The V2.0 roadmap, however, proposes an 18 to 24-month timeline that is highly defensible.
Much more realistic.
If we connect this to the bigger picture, the brilliance of the revised roadmap is how it heavily sequences the physical engineering risks. They are not trying to build delicate quantum bits on day one.
Right, they break it down into logical phases. First, phase A, prove you can actually 3D print this aerogel scaffold and get the superconducting niobium traces to carry a current at 4 Kelvin without breaking.
Exactly. You have to prove the shell works first. Once that's proven, you move to phase B. You build the full spherical shell, map the magnetic valleys, and try to levitate a dummy chip.
A dummy chip.
Yeah, just a piece of silicon with a niobium ring, but absolutely no quantum components. You just prove the Meissner levitation is stable for 24 hours.
And then phase C focuses on the wireless bottleneck. Can you beam microwave power and signals across the vacuum gap to the floating dummy chip without it failing or overheating?
Right, test the communications.
And only after all that infrastructure is validated, in phase D and E around month 16, do you actually place the complex bilayer-graphene qubits onto the levitating chip and try to entangle them. It makes perfect sense. You don't risk the most expensive, delicate part of the project until you've proven the foundation actually works.
Every single step de-risks the step that follows it. And once they validate this single-sphere architecture at the small scale, the scaling path laid out in the document is genuinely astonishing.
Yeah, let's talk about the end game here, the quantum Dyson sphere.
The document describes a system of nested concentric shells. Imagine a massive spherical Russian nesting doll made of these printed aerogel structures.
That is a wild image.
Right. Each shell has its own tuned persistent current pattern. And in the cavities between the shells, you have hundreds or even thousands of these levitating qubit tiles all floating in the void.
Communicating shell to shell using those invisible photonic and microwave interconnects. The document states they're looking at a path to 1 million logical qubits in an assembly that is only 1 to 2 meters across.
And running on just 15 to 45 kilowatts of standard wall plug power.
Which is roughly the power consumption of a large commercial air conditioning unit, almost entirely dominated by that standard cryocooler running the outer shell. We aren't talking about needing a dedicated nuclear power plant to run this thing.
No, not at all. It represents a scalable, physically manageable footprint for a 1 million qubit system.
So what does this all mean? Well, the Quantum Sphere V2.0 takes a flawed, physically impossible concept and uses rigorous math to turn it into a viable, grounded blueprint. We are talking about a levitating, self-cooling, completely wireless quantum brain, shielded from the chaos of the universe by a superconducting magnetic bubble.
The profound shift here is where the boundaries lie. The hurdles for the original V1.0, like that massive heat dissipation error, were violations of the laws of physics. They were impossible.
Right, literally impossible.
But the V2.0 challenges, managing a picowatt thermal budget, keeping the trap servo noise isolated from the qubits, ensuring the niobium films don't fracture on the aerogel, these are strictly engineering challenges.
They're just engineering problems now.
Exactly. They are difficult, yes, but they are solvable. It shows how rigorous knowledge and critical thinking can take a sci-fi fantasy, strip out the impossible, and distill it into an achievable roadmap.
It really does. And it leaves you with something fascinating to ponder long after you put your phone down today. If we can engineer a way to perfectly isolate and control a highly sensitive computational system floating in a vacuum, powering it and cooling it, using nothing but microwaves and photons, what other sensitive human technologies could be completely revolutionized? If we just figured out how to cut their physical ties to our noisy, vibrating world, what else could we make float?